Right. We are on. Um, Leo, thank you so much for being here today. Leo is a speaker who I've been very excited about coming. He needs very little in the way of introduction. But as you can see on the slide here, Leonardo de Moura is the senior principal applied scientist at AWS, where he's known for many things. I think if top of mind for me are being one of the big developers behind the Z3 theorem prover, and as well as I think most of his efforts now are being put into Lean. And I'm very excited about this talk because one of the things that I'm excited about Lean for, and this is a space that I want to learn a lot more about, is the meta programmability and proof automation. And from what I understand, the grind tactic is sort of a really big piece of that and has a lot of capabilities that we typically think about as part of SMT solvers or sort of more automated methods, sort of integrated into the Lean framework. And so I'm excited to hear about the guts of that and see what we can learn as folks who use some of these data structures for different purposes. So yeah, I'm very excited about this. And Leo, when you are ready, please take it away.
Thank you. Thank you. Very happy to be here. I want to tell you today about the grind static. Okay, grind is in the context of Lean. Lean is an open source programming language in proof assistance. It is very extensible, right? Lean is implemented in Lean. Everything. I mean, the LSP, the parser, macro, metaprogramming framework, the code generator, everything. Even the build system and documentation authoring system, they are also implemented in Lean. We have a small trusted kernel. You can export your proofs and check them with independent checkers. And if you want to learn more about Lean, you can go to our websites. Lean is based on dependency type theory. Uh, Here's an example from Kim. It's an index map. I think it shows really well why it's called dependency type theory. Here, index map is a polymorphic type. You have a key alpha and a value beta. And alpha should, these are type classes, it should have a Boolean equality and a hash function. That's the meaning. And this, this information will be synthesized using type class resolution like in Haskell. A index map is like a hash map that you remember the order things have been added to the map. In this way, you actually have a mapping from the key to a natural number, the position where the key is, and you have the keys is an array, and values is also an array, right? The three first fields are standard, right? In any programming language, would be something like that. But the next two, they show why it's called dependence type theory, right? So, I mean, these two fields, the type of these fields depend on the value of the previous fields, right? And you can view them as invariants for this data structure. The size keys is saying that the two arrays, keys and values, should have the same size. And you can tell Lean how to synthesize these fields if the user, if you do not provide a value for this field, you do not provide evidence that the two arrays that have the same size, Lean will try to synthesize using grinds. And we also have the last field is also showing that it's basically a consistency between the indices fields and the keys one. Basically saying if you have an index I and keys at I contain some A there, then if you go through the hash map indices, you get back to I, right? And again, you synthesize using grinds. The full example is available online. But let's see how the automation works. Then you have the insert function that you get an index map. You are trying to insert the key A with value B and produce a new index map. And here, lawful Boolean equality is just an extra condition so that your Boolean equality, if it returns true, the values are indeed equal, right? So, I mean, it's not a bogus equality, right? And this function, you only have the properties you expect if this is the case. And you do a match on you check what is stored as position A in the field indices. If you have an index there, I, you just you don't update the field indices, but you update the value of the keys at position I and the value and the data in the field values, right? Also at position I. Otherwise, you just insert, right, new elements in these arrays and you update the hash map. And you notice that no proofs were, you did not have to provide proofs that the sizes are still the same and the indices and keys match each other, the behavior, right? The proofs were all done automatically using grind here. The next thing, this example that I found really cool that Kim did is made it clear that there is a difference between library building time and library use time. The theorems you need for building the library are different from the theorems you want your users, the library users to have access to. And Kim did that. Basically, he marked, the, they marked these definitions of told grind. You feel free to unfold these definitions while proving these theorems. He puts this modifier local. The scope here, grind will only do that inside of the file defining index map, right? And this is great because you don't want to, when people are using the library, you do not want to break the abstraction, right? You do not want Grind to keep unfolding these definitions in wasting time with implementation details. You want for the library users, you want to use these theorems. You're not tagging them with the attribute grind saying, these are terms that you should use when you're trying to prove things about index map, right? Are the usual terms, right? Saying that uh, uh, if you try to find something and get the index, if you insert something and you check if it's there, it is there, the usual terms, right, that you want when you're using this kind of library. Uh, Before I make the second point, I think most of you probably know that proof of systems are like a computer game, but I want to emphasize that especially because of AI. Uh, in Lean, like many other proof of systems, you can view it as a computer game where the moves in your game are called tactics. Grind is just one of them. And you usually have a view of the game board where you see the state of the game. Why this is relevant, right? Is because AI now are starting to play this game. Before we go into AI, let me tell you a little bit about the philosophy, the design philosophy we use to build Lean, and it's the same one we use for building grinds, right? The first one is to listen to your users, right? I mean, for example, Lean embraces classical logic and classical mathematics because that's what our users care about. Lean is a programming language, right? You can be constructive when it matters. We also want grind to be extensible the same way Lean is extensible, right? I mean, many people ask why Lean became popular. We believe extensibility was a big deal. The math community, MathLib has 2 million lines of code, the Lean mathematical library. But 50,000 of these 2 million lines are Lean extensions, right? They wrote their own tactics, their own automation, linters, you name it, right? Notation and so on. And another design philosophy is exceptional tooling. That's how we scale, especially in MathLib. Keep in mind, MathLib has more than 600 contributors. These people never met each other. How can you have a coherent library when you have so many people contributing code? Is with tooling, right? Linters that will ensure that you're doing the right things, you're not making silly mistakes, right? CI is important, user experience, the build system, caches, this is all important. And in grinds, we want to follow the same playbook. Exceptional tooling is essential. and all components work together. This is going to be a recurrent team. I mean, we want to benefit. When someone improves, for example, how you visualize traces in Lean, we want to leverage that. When you're visualizing grind traces, you're going to have the same benefits. When we improve the code generator, grind will be faster automatically. When we change the the code action mechanism, make it better, grind will benefit automatically. We want a unified system where all the pieces fit together, right? And when one piece is improved, the whole system is improved.
Leo, can I
Mhm.
interrupt if that's okay?
Yeah, yeah,
Can we go back about 3 slides, I think?
yeah, huh? This one?
Yeah, yeah. So here, the by grind is really interesting.
Uh-huh,
This is sort of, I guess, an annotation that in the absence of an implementation of this, you can try to generate by invoking grind. But if the user, for whatever reason, for a particular instance, needed to, like if grind didn't work or they wanted to,
uh-huh.
for whatever reason, can they just write the proof manually and then this only gets
Oh,
double
yes.
the backup?
Yes, yes, yes. By is the way in Lean where you switch to static modes. This, we are just calling grind that is static as like any other. It could be, for example, in the game. Let's see
Uh,
this one. You see the by keywords. You're
yeah.
calling intro, simp. Uh,
But if you go back maybe two now to the
mm-hmm,
type class definition, so
mm-hmm,
index map is not a particular implementation, right?
yeah,
This is a class.
yeah,
And so when you're doing, it's interesting. So like when you're doing these by grinds, I guess after you do the resolution, like when you are deriving an instance, then if the pieces you don't need, like size keys, well formed, or the
yeah,
library code,
yeah.
by grind is sort of a default way to try to synthesize.
Yes,
So you're sort of
yes,
programming a synthesizer, and
yes.
user can override it by providing particular
Yes, yes,
implementation. I see.
correct, correct. And you could use here by anything. Can be by
Right.
simp, by Aesop, you by raffle. Sometimes people, I see lots and lots of users, they have by raffle as a default.
So there's this, I guess what's interesting is there's these multiple, we often think about like proof time, build time, run time. There's this other set of synthesis things happening during type class resolution time, I guess. So like I'm trying to understand the full stage of what code gets generated when is kind of tricky here, but I guess it doesn't matter. It's all gonna get type checking work. The other question I had, if you go forward to the design slide, the design, yeah, back one,
Oh, so sorry, sorry, I went
or
too far.
oh, sorry, maybe forward
Yeah,
one, maybe forward one, and
uh,
maybe oh,
I think it was this one,
this
right?
one, yeah,
Yeah.
perfect, perfect. So this was actually very helpful. I really like the big picture. Um, some of these are intention, like exceptional tooling, I think always helps everybody, but extensibility and unified are often intention. That is when users can add new things to the language of the system, then
Mhm.
maintaining a unified, coherent thing is really challenging. Are there things
Yes.
in the lean community that have arisen, or is it just kind of Leo is the sync point and Leo has
No,
everything
no,
in his head and therefore can keep it unified, or is there some other
no,
way that things stay unified?
no, 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 no. It's not. I mean, especially in MathLib, I have no role there. I mean, they maintain themselves. They have their own linters, their own coding standards that are enforced by linters. Uh, they have tooling. For example, your him recently built a tooling for checking if your simp annotations are coherent, and is run during the CI. Having whenever people build tools for checking if the annotations in the library are coherent or not. Uh, for example, one thing that one blasphemy is would be like if you can find non-confluence. I mean, he writing rules that are going to different directions and they never get back. It's not you do not
Right,
have the diamond property.
right.
So depending on which things you import, you'd get a different normal form. And making sure, ensuring your simple annotations is giving you s- a confluent rewriting system. It's a great property to have. And if you're breaking this property, you have to have the allowed list saying, I'm
Yeah.
allowing to break it here. But you, as the library designer, knows it. And if someone breaks it, someone gives a contribution to Mathlib that breaks this assumption, you're going to be notified by CI. I think that's the kind of tooling that's really important. Nobody will keep doing manual checks after each PR to ensure things are confluent, right? You will not
Doesn't
scale.
scale. Yeah.
Yeah.
So that's a great example. And like normalization, I think sort of is a perfect way of showing how uh, tooling and design taste, et cetera, with combined help ensure uniformity. But
Yes.
one example you gave was on the code generator. And there I imagine there are things that are really unsat. Like you have to make these design choices in the code generator, and it's going to make one person's automation faster and somebody else's automation slower. Or it's going to make so are there things there that also help with unification, or is that just because of the math focus not as much a problem so far?
Yeah. So far, it's not a problem, but I believe if this becomes a problem, one thing that we have in our code generator, because it's implemented in Lean,
Mm.
there is one thing that's called probes. You can write a probe, is a piece of Lean code that you can install after any pass that will check for properties in the IR, right? And you can write something that checks if your expectations holds, right? So, I mean, suppose that you expect that some optimization has been applied. You can write a probe that will check the IR to double, yes, it has been applied.
Ah,
Because it's something that's for functional languages, the amount of optimization is applied is dramatic, right? I
yeah,
mean, comparison with an imperative language.
yeah.
And sometimes in functional, the same way this is awesome, sometimes is awful because for some strange reason, the optimization is not applied. And now you get a performance hit. But with the probes, you can check, you can inject code that will check if the optimization has been applied or not. You can visualize, you can put probes that check the size of the code after some pass. I mean, you can have all these sanity checks in your CI.
And now they become CI failures, which means that
Yes,
you scale. That makes a lot of sense.
yes,
That's
yes. Yeah,
perfect. That's a great
yeah,
example. Thank you so much. Yeah,
yeah.
yeah, that's great.
Uh, but this is a question now that I get all the time. Why do we need proof automation? AI will prove all the terms for us, right? I mean, I get this question all the time. I mean, for example, especially after last summer in 2024, when Google DeepMind released Alpha Proof, they got a silver medal level using Lean. And now in 2025, both DeepMind and OpenAI got a gold medal using informal reasoning, and ByteDance and Harmonic a gold medal using Lean. And you may feel like, well, why do we need proof automation anymore? This AI will do all the proofs for us, right? Well, the first thing is that AI is playing the game, right? They are using the moves. The moves are tactics, right? I opened one of the proofs that was generated by Alpha Proof last year, and they are going to find simple uh, Z-Fi. Z-Fi is something that maps things to the integers. For example, you have problem about the natural numbers, we will convert in the problem on the integers. You have norm num, NL arith, that's a tactic for nonlinear arithmetic. These are all moves that's the AI plays in the game, right? They are using the proof automation that has been built using standard automated reasoning techniques. And we have to keep in mind, if you provide better moves, the AI will be more powerful automatically, right? These two, building proof automation and AI, they are not in conflict. They complement each other, right? But before we talk about grinds, why proof automation is so hard for Lean and any system that uses dependency type theory? Right? Dependency type theory is awesome. For example, array get is a cool example where you're trying to access an element of an array. You provide evidence that the index is in bounds. You don't need any runtime check. This is great. This is also great for the compiler uh, because imagine if you do not have the proof term there and your array gets is correct because you're inside of if then else, and the proof depends on the condition of the if then else. functional compilers, they float code around. But here we know the array gets, you cannot float the array gets outside of the if the proof depends on the condition of the if then else, right? It's not, if you did not have that explicit in your code, the compiler would have to reprove to float code around. It would have to try to prove again outside of the if then else, right? And here the compiler knows whether it's safe or not. This is great, but it creates problems. Suppose that you have this term, array gets, you're trying to access position 2 plus I minus 1. This happens especially when you're inlining codes, you're going to get some funny things like that. And you may feel like, oh, okay, this can be simplified to I plus 1. But the problem here is that age is a proof that 2 plus I minus 1 is less than AS, the size of the array, right? Uh, if you write the term like that, this is a typing correct term. Age is not a proof that I plus 1 is less than the size of AS, right? Uh, there are millions of little problems like that. In Lean, this is fixed by creating custom congruence theorems automatically that adjust the proof age automatically for you. But these are things that you have to keep in mind, right? Even congruence is not as trivial as in the first order case. Another complexity is type classes. I think I can skip. I mean, I think most of you know. I mean, you are a bunch of PL folks. I mean, the first thing type classes, especially in Lean, is that you have diamonds, right? It's like here you have a semi-group. You have two subclasses, monoids and semi-group, commutative semi-group, and we have a commutative monoid that inherits from both of them. The main problem here is that you have two different ways a commutative monoid is a semi-group. And these two paths are definitionally equal, but they are different terms, right? And the proof automation has to realize these two paths are definitionally equal, right? It has to do that, it has to handle that when you're doing, especially when you're doing congruence closure, right? These two fields were not going to hold by congruence. They're not be equal because of congruence, because they're going to be equal because they're definitionally equal. And checking definition equality can be arbitrarily expensive, right? You are basically doing symbolic evaluation, and you have to balance costs of doing this reduction and these checks with the precision of your proof automation. Another problem is the scale, right? In Mathlib, for example, we have more than 1,000 classes and more than 20,000 instances, right? And you have to keep in mind that type class resolution is backward chaining. Each instance can be viewed as a horn clause, right? Where this is the conclusion, these are the antecedents. Lean uses stable resolution to address the diamonds, especially when you have a chain of diamonds. You want to avoid exponential behavior and to avoid this exponential search. We use stable resolution. But any proof automation you build has to be able to handle these diamonds too. Another problem are the Russian dolls we have in Mathlib. I have one example here where you have a class that has two parameters, R and L. They are types, but R is not a arbitrary type. It's a type that's a commutative ring, and L is a Lie-admissible ring. Basically, you're creating a class where the parameters depend on other classes. That's why we say it's a Russian doll. And sometimes you create another class in Mathlib that has Lie-admissible algebra as a parameter. And so you have several layers. It's like these Russian dolls. You keep a class that depends on another class, that depends on another class, that depends on another class, right? And this creates massive terms in your proof automation. You have to handle them. Another question we get is if Lean has hammers. Yes, Lean has the Lean hammer being developed as CMU. It's like an umbrella of hammers. One of them is duper, is a superposition prover that's used for reconstructing proofs built by automated provers like superposition. We have BVD sites develops that the link flow is the fastest verified bit blaster around, uses CAD-Cal. We have Lean SMT develops at University of Minas Gerais, Stanford, and University of Iowa. It's called CVC5. We have Lean Auto. There's a common infrastructure for converting dependence type theory in high order logic. And make it easier to call provers like zipperposition and CVC5 is a common framework that many people are using now to be able to call their favorite automated prover from Lean. But today I want to tell you about Grind, right? Grind is a new proof automation being developed by Kim Morrison and myself. It's based on SMT techniques. In SMT, I think the right mental model, you should view it as a virtual whiteboard where you're putting new facts there. You have the core of these SMT solvers is always a E-graph where you have the equivalence classes, the congruence classes, and you use e-matching to instantiate theorems. And you have theory solvers like for arithmetic, commutative rings, and so on. And we want to support dependent types and type classes, dependent pattern matching. This is what Grind is, but it's also important to tell you what it's not. Grind was not designed for combinatorial problems, right? If you're trying to solve huge combinatorial problems, we say in our minds, the right tool for this kind of job is to call SMT solver or a set solver and have a specialized checker. For example, BV decide is calling a set solver. The set solver creates a LRAT proof. This is a custom format that's optimized for set proofs. Some of these proofs are megabytes, even gigabytes, and some extreme cases like from Iron Oil, from CMU, is a terabyte, right? And it's completely impractical to translate these proofs into a lean proof term. There's a generic proof term that can be used to express advanced math, anything, right? For this kind of proof, you need specialized checkers like we did for BV Decide. We wrote a specialized checker for it. But here we're shooting for making a very extensible engine. We're building lean proof terms, right? And the case analysis is handled using the cases, the, the recursors we have in the kernel, right? And it should not scale for huge combinatorial problems. We want to make sure that we can handle trivial problems using grinds, problems that people are too annoying to build by hands, right? Especially chaining. Sometimes people have to do, oh, I do simp, then I do this fact by hands, then I call omega. With grinds, you can collapse all these steps in a single one, right? And you don't have to remember all these little tactics to put them together. This way, our design principles are we want support uh, to have native support for dependency type theory. We don't want to tell our users, oh, you cannot use dependency type theory if you want good automation. You want to solve trivial goals. We want fast startup time. You don't want to spend an insane amount of time pre-processing, monomorphizing your goal. We want to process it as is, right? We do not want to depend on mathlib, right? Grind should, of course, it supports mathlib, but if you don't have mathlib, you're not using mathlib in your project, it should work, right? We should have rich diagnostics. It should be configurable, extensible. We should have support for grind question mark. Grind question mark in Lean, we have these question mark tactics that they produce a residue. They make a suggestion that allows you to replay the tactic more efficiently. And we want to follow the same idiom that's used in other tactics like BV decides and ASOP. And we want to provide pre-annotated standard, the standard library mathlib, we want them to be pre-annotated. The architecture is basically we have a pre-processing
Leo,
step.
can I ask you a question real quick?
Yeah, 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 yeah.
So I mean, I think this, it's very smart to lead with some description of what grind is not, right? Because
Yeah,
there are these specialized
yeah,
solvers
yes.
that, like you said, have not only a lot of capabilities, but it's complex to like grind is doing something different, right? It's
Uh,
dealing with dependent type theory
yes.
natively. I'm wondering, like, sort of in the limit, right? Given the sufficient engineers and so on, right? Like, uh, would there be any benefit to bringing more and more of that into native Lean? Because as you said, it's a fully capable programming language, right? Like conceptually, one could re-implement anything that they're doing in Lean.
Mhm.
Like, would you get any benefit from a sort of more native binding, or is the fact that you have to do these like sort of proof translations a cumbersome enough interface that there's no point?
Let me give you an example. For example, because we want flexibility, in grinds we decided to use uh, uh, pure functional data structures, right? One great property of them is that it's really easy to fork your states, and you can work on them in parallel if you want. Most SMT solvers they use they use imperative data structures, and they have a trail that is executed to backtrack. What it means in a regular most SMT solvers, you can work only on one active state. Basically, if you want to work on another branch, you have to execute the trail and move to the other branch, right? So you have to undo the operations you have done in this trail. By using pure functional data structures, you do not have this restriction, right? It's really easy to take snapshots of your state and say, okay, I'm going to save here. Oh, you can give this state to the user without any compromises about, oh, the user has to update the trail correctly. It doesn't matter. You gain flexibility, but you pay a price in performance, right? It's like this trade-off. SMT solver follows a very specific architecture, optimized for performance, but sacrifices flexibility. In grind, we made a different decision. We want maximum flexibility, extensibility, and most things, especially in software verification and math, there are cases where you need to do a massive case analysis, but for that cases, we want to use specialized statistics like SMT, solvers, BV size. Most of the time, you do not. It's really rare for your proof or something you're trying to prove in your program to have to, for it to be correct, you have to do a massive case analysis. It's super weird, right? I mean, there's something wrong about your algorithm that is so many cases to justify why it's correct, right? It was designed by a human to begin with. There's probably a simple reason why it's correct, right? In math, if the proof is sometimes it happens, but most of the time you have a beautiful proof, right? There are beautiful reason why that's true, right? And we want to find this kind of proof of grinds, right? We want to automate. That was the trade-off. And keep in mind, SMT solvers, they are used a lot in scenarios that we don't care in grinds, in Lean. For example, one of them is test case generation, white box fuzzing, like Sage. In white box fuzzing, you're trying to find you basically enroll a real program, right? In the case of Sage, for example, would be x86. They are symbolic simulating a huge trace in your program and trying to find the input that would trigger this memory access violation, right? It's a huge bit vector problem, right? The problems have megabytes sometimes in size. is like a combinatorial problem by nature. It's very different from here, right? Where we are trying to prove something. You want a modular proof, right? I mean,
Right. Okay, that makes a lot of sense. Thank you.
uh, and we have preprocessing, internalization, that's the process of converting linear expressions into the solver's internal data structures. We have the graph like SMT solvers, the graph in the core of grinds, and the satellite solvers. We have solvers for linear integer, arithmetic, commutative rings, linear arithmetic, AC, and so on. Uh, Two of our solvers use this model-based approach, where you're trying to construct a model for your constraints. And whenever you find a conflict, you try to resolve using something, using a conflict resolution that's more or less like quantifier elimination. This is a generalization of the techniques people use in SAT, right? And we use that in grinds. One advantage of these techniques is that they are easy to implement. They're much easier to implement than a solver, for example, for linear arithmetic, using a solver based on simplex, for example. It compacts the code, you get nice proof terms. That was our main motivation for using these model-based solvers. But one new thing that we have in grinds that they are parameterized by type classes, right? For example, it's not just for linear integer for linear. It's not just for the reals and the rational numbers for the integers. They're parameterized by type classes. And for example, this was motivated by a request by Turnstile when he was trying to prove something about ordered vector spaces, and he was frustrated that linear riff did not work. But there's no reason for it to not work. I mean, you can adjust the decision precision a little bit, and it will work. In the case of grinds, it will work. I mean, order vector space is an integer module. It has a linear order, and that's it. That's what grinds by the type classes. It figures out that ordered vector spaces implement these two type classes that grind knows about, and it adjusts the implementation and is now a decision procedure for this case. And you can solve it automatically. Basically, in the core linear repository, we have a collection of type classes like integer module, linear order, partial order, and so on. Grind knows about these type classes. And we provide instances for the basic types we have in core. But then in mathlib, we configured mathlib to say, oh, order vector space is an integer module defined in grinds, is a linear order, and so on. And everything works out of the box. The message here is that you can configure the solvers that's implemented in grinds by just providing instances to these type classes. And same thing for for cut sets, that's for linear integer arithmetic. We have type classes called toInt that allows you to tell how a specific type can be embedded into the integers. And this is useful for integer 32, for bit vector 64. You just tell grinds how to map these types into the integers, and you use a procedure for the the cut set. That's a procedure for linear integer arithmetic, and and it works out of the box. I mean, for example, it works for integers, of course. The procedure is for the integers, but if you have uint32, it works because you have the toInt class properly instantiated for this case. For fin4, is a type that contains just 0, 1, 2, and 3. And grind knows now. I mean, we have a toInt instances for fin. It will know how to map this problem here in an integer problem, and will work out of the box. We also have a solver for commutative rings and fields. It's based on Grobner basis. It's also configured by type classes, right? We are not doing it for the complex numbers, right? We don't even have the complex numbers defined in the core lean repository. They are defined in mathlib, right? And you have many different type classes to configure this solver. And the cool thing is that it adapts itself. I mean, if it's a commutative ring, this is actually true. I mean, grind proves automatically. If it's a field, it knows you have an inverse. You can have you say, oh, it's not just a field, but it's a field of characteristic 0, right? Grind will take advantage of that. Bit vectors, this is not being solved by bit blasting. Grind knows that bit vector is a commutative ring. It knows also that it's a commutative ring with the characteristic being 2 to the 16, right? It will take advantage of that. And this solver was cool because I was really happy because Kim joined the Lean community like 10 years ago. At the time, Kim was working on quantum computing, uh, and they had a paper where they use computer algebra system. And this is like blasphemy for a mathematician, right? If you have a paper where your proof relies on a computer algebra system, it feels like you are cheating. I mean, these computer algebra systems may have bugs, and this is one of the examples there that were in the paper, right? And now it's solved in milliseconds by grinds, right? This example, you have a proof at the end that can be checked not just by our kernel, but by independent checkers, right? And this is not a toy example. I mean, uh, this kind of solver that computes a global basis, they can, in a computer algebra system, they would generate a null Stellensatz certificate. The null Stellensatz certificate for this problem has thousands of terms, right? Thousands. I mean, it's like, I think with Mathematica, the certificate would be 10,000 polynomials with 10,000 terms, but our implementation is not using a null Stellensatz certificate, otherwise it would be thousands of terms too. We compute a derivation, and we can prove this stuff in milliseconds, this example, right? We also have solver for associativity. If you have associative operators, it's also parameterized by a type class. The basic is just associativity, but optionally you can say that it's also commutative, is idempotent, and has a neutral element, right? With this additional type classes, and it would also adjust itself. And the main motivation for this solver is to it's the first building block to have AC support for a matching modulo AC. You need to have a AC solver there. I mean, otherwise you're going to instantiate your theorem, but you cannot reason efficiently about AC. And if you use, I don't need to tell in this audience that if you add associativity and commutativity as in matching theorems, you create so many instances, right? And with this kind of solver, you can avoid marking the terms as for a matching. You handle them with the solver, right? For a matching, right? I mean, okay, I think I can skip. Just tell. I don't need. I think I don't need to explain to this audience what a matching is. But why is it in grind? Because it's a really useful way to instantiate terms automatically using the virtual whiteboards idea is like it's a way to instantiate theorems and putting new facts on the whiteboard, right? Imagine is very effective, and it works great. For example, in this example here, matching is adding this fact that the cosine square plus sine square equals 1 to the whiteboard. After you have that in the whiteboard, the solver for commutative rings will kick in and will close the goal for you automatically, right? It's like matching congruence close, everything working together, right? In this example, uh, this is true because I mean, if you expand, you get cosine squared plus 2 cosine times sine x, right? Plus sine square. right? But we know the cosine plus sine square equals 1, and that's why this is true, right? And that's why you need to bring these facts. But this here is just showing that's why matching is relevant here. It's a way to bring new facts to the whiteboard, right? But matching creates problems for dependence type theory, right? Uh, uh, I have this minimal example here where we have this p-binds. For the sake of time, I will try to move a little bit fast, but I'm happy to talk offline about it. Uh, Here, I have this theorem, p-bind sum. Let's assume that we had marked this theorem for a matching, right? This p-bind sum. We are saying that p-binds of sum A f equals the right-hand side here, right? But f here, the type of f here has a proof saying that uh, for some argument here, you're going to have sum A, the O, right, equals to the sum A prime here. In this particular example, H here is saying that X equals sum A, right? But then, because of fee matching, you may say, okay, this theorem, I can instantiate this theorem. I mean, if this is the pattern, this pattern, modulo equalities, is an instance, right? You have the equality X equals sum B. This way, you you can match this ground term here with this pattern, modulo equalities, right? The problem is that the result is not type correct, and grind puts a casting operation there automatically for you. But in this particular case, casting over a function is devastating for dependence type theory. There's very little you can do after you have a casting over a function. And the proof will fail in this case. But in grind, we can handle generalized versions of this theorem here, right? Instead of writing using sum A here, we just say, no, it's a X. And X is equals to sum A. And we use the same matching algorithm. That's now we can remember that when you're doing matching, you traverse equivalence classes. You know actually the proof. You know when you're doing matching, you know why the term you're matching, right, against, why it is equals to sum A, right? You have this information there, and grind exploits that. And if you have the generalized theorems, grind will be much more, matching will be much more effective. No typecasting will be introduced, and the proof will go through automatically. Uh, let's talk a little bit about extensibility. We have seen one form of extensibility. You can decorate theorems with grind annotations. No, sorry, we saw the type classes. I mean, we can configure grind using type classes. We saw that we have attributes, the attributes grind, but you have modifiers, right? We can say, oh, when you use grind equals, just saying use the left-hand side of the equation as your pattern for matching. When you use the the arrow, you are saying use the antecedents as a pattern, right? So you can instruct grind, and you can also provide the pattern manually. But this is a convenient way to provide the patterns. You can also implement your own propagators. This is a piece of link codes. This is actually part of the grind implementation saying how you propagate. For example, when you have an OR application, these propagators are invoked whenever one of the children, uh, something happened with the type classes. Like you merge the type class, you merge the type class, you have a child of this OR application of one of the children, the type class has been modified. You added new elements to the type class. Then the propagator is invoked and you can do something. For example, in this case, we say, okay, if A is in the equivalence class of false, I can propagate that A or B equals B, right? If A is in the equivalence class of false, and so on. And you may point out, well, okay, you're missing one case. If A and B in the same equivalence class, you can propagate that A or B equals A, right? Yes, no problem. You can add this propagator if you think it's useful for your problem, right? You can add new propagators if you want. The other thing you can do, you can add your own solvers, right? Uh, you do that by 3 steps. You first define the state of your solver. This is actually the real state of the AC solver for associative and commutative operators. Then you say, oh, I want to define a solver extension. And you just say, I want to register a new solver extension. You say, this is the state of my extension, and I tell you how to initialize it. In this case, it's just the empty state. I mean, you see every single field has a default value. We're just saying, okay, initialize with the default value for all the fields. Then you define handlers. Here I have the handler for whenever you learn a new disequality in the core, it will communicate the solvers, and the solvers are going to execute some code. And after you define your handlers, you just initialize your extension, say, okay, for internalizing terms, this is the function you should invoke. When you learn a new equality, this is the function you should invoke, and so on, right? You you can attach if you have a Lean project, you can define a solver in your Lean project and attach it to grind, and grind you will invoke it automatically. This is useful for many different reasons. I mean, for example, I told you about we have solvers for that do bit blasting, right? Uh, you may feel like for my projects, it would be great that I use grind a little bit, but if it's stuck before failing, let's call BV decide, right? And you can do it with this plugin interface. Oh, I have a solver for string theory, right? For regular expressions. I mean, we do not have a solver for that in grind. You can attach it here, right? Tooling, right? Tooling to maintain the grand challenge is how we told you. I told you about these annotations, right? How do you maintain these annotations in a coherent state when you have 2 million lines of code in Mathlib, right? And people will be putting annotations all over the place. You know that with matching, right? It's really easy to create unbounded chains of unbounded number of instances where unbounded number of instances are created. And this is bad, right, for performance. And one idea we have is, okay, we can write tools. For example, this is a script written in Lean that it go over all the match theorems you have. And it creates a scenario where you instantiated this theorem once. And after you instantiate this theorem, it sees how many other theorems are going to be instantiated after that. You can use that to detect unbounded chains, right? You can see nest interactions between different theorems. And you can have in your CI these scripts running and checking for the consistency of your annotations. If someone adds a new annotation that does something horrible, right, you're going to catch. You don't have to keep checking manually. And this is important because, like in the simp case, there's a non-local properties, right? It's a nest interaction between two different theorems, right? And you want to catch that automatically. You don't want people checking these things manually. Another thing is when the tactic fails, some proof assistants they call hammers, they call SMT solvers, first order provers. Hammers are great, but when they fail, you have no idea, right? There's no information whatsoever. In grinds, we have this grind diagnostics. It's like use the trace infrastructure. You can fold and you can search these traces, and you can probe. For example, you can check the counter example in the linear integer solver. You can see the state of all equivalence classes. You can see which patterns have been used for matching. You get statistics about how many times each theorem has been instantiated using a matching. You get diagnostics. You can inspect and see what went wrong there. For example, one common thing we do when something fails, we go over the equivalence classes and check, well, I expect these two terms. We expect grinds to learn that these two terms are equal, right? And you can check by just expanding the equivalence class tab, right? Uh, and the same for structure, I mean, because our traces are interactive, for example, if you hover over elements, you get the type. You get a type for, for any elements. You can go to the definition of this theorem. We do not implement that. We are just piggybacking on the infrastructure for tracing that is available in Lean. And for example, Mark Huizinga is implementing support for searching the traces. He's merging this feature now. And now it's not just the traces for simp, for definitional equality, but also for grinds. It works out of the box. People will be able to search the trace produced by grinds automatically, right? This if normalization, I think just for sake of time, I mean, we're running out of time. I will not talk about it. It's just an example that Rusan Leno Shankar came up with for challenging. And with grinds, we can do it in a single line, right? I mean, the proof is just one liner now. Try question mark is automation we're building today to not just call grind automatically, but call to be a plugin infrastructure that people can attach their own automation, and is a convenient way for people to learn about automation that's available in Lean and to invoke it automatically. And with code actions, you can replace. I mean, so you could try, it proves and says, oh, use fun induction with normalize and then call grind in each sub-goal to finish the proof. The initial reactions have been very positive, both in software verification like Marcos and Fabricio, but in math, I mean, people are reducing big proofs in mathlib, converting them to one-liners. Terence Tao has been using grinds with, and now he knows about susceptibility modular theories. We were very happy that he's using it. The roadmap, we want to add AC matching, more tooling, right? We want to add this parameter minimizer. We want, when grind works, we want to tell you you should only use these solvers, only these theorems for matching. This is the minimal set that allows you to solve the problem. We want try question mark to be a hub for all proof automation in Lean, even the AI-based ones. We are trying to build tooling to help mathlib to annotate the mathlib community to annotate mathlib. We are adding support for nonlinear inequality to grinds. I mean, the commutative ring solver is for equalities and disequalities only, and the linear integer handles inequalities, but is linear, right? It has no support for nonlinear. And drove me. We want to be able to handle this example that I was demoing to hedge funds automatically. Just I could do it with grind, but I had to write 4 lines instead of one, right? We can do it in one line if you have basic support for nonlinear arithmetic. And people may ask, well, this is a good example for AI, right? AI can create these scripts. Yes, it can do it, but it's way more expensive than having a simple heuristic in this case. AI is great for the cases where it's really non-trivial, the proof. But here, I mean, a simple heuristic would do it, right? And I'm over time, but I want to emphasize tooling is essential for scalability, right? It's the only way to keep a library, a coherent library, especially when you're adding annotations for simp. simp is a much simpler tactic than grinds. And the only way we manage to make it scale is with tooling, right? Same thing will be true for grinds. We need much better tools. And yeah, thanks a lot for your attention. Grind is a new extensible tactic based on SMT techniques. We want try question mark to be the hub for all proof automation lean. We are working on better tooling, right, for making things more to help us to scale, right? So we want better tooling to be able to replay grind proofs more efficiently, find problems with the annotations automatically, and maybe even in the future, right? If you are uh, 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 some AI experts believe if you have tooling that tells you if the annotations are good or not, you'll be able to build the AI that comes up with the annotations automatically, right? Because then you can create a feedback loop. The AI comes up with the annotations. Now it can execute our tooling that will tell which annotations are creating problems, and it can keep self-improving until it comes up with something that works well in practice, right? Thanks a lot, folks, and the slides are available online. Thank you.
All right. Thanks so much, Leo. I'm going to stop the recording, but if folks want to hang around, or Leo, if you have time, I'm sure there are
Yeah,
plenty of questions.
yeah.
Goodbye, you